Hey, this is the video walkthrough of the motion and speed big ideas. So in this unit, we talked a lot about position time graphs, which is just a way of saying where were you at what time, and you can figure out speed from that too by looking at the slope. So distance is always going to go on the y-axis, and time is always going to go on the x-axis. Okay. You can determine an object's position from a distance time graph because they're always going to start at zero. I mean, the 0 point is like the starting point. And then you can always see how far they are from where they started based on the y-axis. So at 1 second, they were 10 meters from the starting line. At 2 seconds, they were 20 meters from the starting line. Basically, yeah, look at the y-axis. It'll tell you how far they are. At what time? Yeah. At 3 seconds, they were at 30 meters from the starting line. And the y-intercept shows where they're starting at. So we have the 0 point is actually the starting line, but this person got a head start. So at 0 seconds, they were 10 meters from the starting line. So the y-intercept tells you where they're starting at 0 seconds. Okay, how can you tell an object's direction from a distance time graph? If there is a positive slope, that means that as time is going by, they're getting farther and farther from the starting line. So that is a positive direction, positive slope. And if the line has a negative slope, then that means as time is going by, they're getting closer and closer to the starting line, meaning they're traveling backwards towards the starting line. Okay? What is next? Then there's the speed. The speed is the distance an object travels in a certain amount of time. Okay. So you can determine speed by the slope of the line. So we have here a pretty slow speed movement. So they're only moving like 2.5 meters every second, looks like. In comparison to this one where they're moving 10 meters every second. So we're always looking at rise over run. So I see here that like in 4 seconds they moved 10 meters. So I could do 10 divided by 4 to find that 2.5 meters per second. Whereas here I can look at 10 divided by 1, so 10 meters per second, or 40 divided by 4 is also going to give me 10 meters per second. So the steepness of the slope determines the speed, or tells you the speed. Yeah, so this is just what I was saying. A graph with a shallower speed represents, or with a shallow slope, represents a slower speed, because they're not moving very much distance in each increment of time. And then a graph with a steeper slope represents a faster speed. So yeah, higher slope or steeper slope means that they're moving more distance in a less amount of time. So when you see a horizontal or flat slope there, that means on a position time graph that they're just not moving during that time. It's like this first second they moved a certain amount of speed or a certain amount of distance, but then their position is not changing as this time is going by. So this is a time when they're just holding still. Okay, and if we want to calculate this, we can use an equation triangle. And to do that, we just cover up the thing that we're trying to find. So if we're trying to solve for time, we cover that one up and look at distance divided by speed. If we're solving for speed, we do distance divided by time. If we're looking for distance, we do time divided by, or time times speed, right? So if they're above each other, it's going to be a division. If they're next to each other, it's going to be times. Okay? Can you calculate an object's speed from a distance versus time graph? You absolutely can. To calculate the speed of an object, you need to know how much distance they covered in a certain amount of time. So For example, there's two different speeds going on here. So from 0 to 2 seconds, the runner traveled from 0 meters to 10 meters. So 10 meters in 2 seconds is going to be 5 meters per second. And you can actually see that if you look here. At 1 second, they had traveled about 5 meters. But then from 2 to 4 seconds, the runner traveled from 10 meters to 40 meters. So we can say that the runner traveled 30 meters in 2 seconds. So you want to be careful. We're not looking at this. We're just looking at this triangle right here for this distance, right? So they traveled 30 meters in 2 seconds. So 30 divided by 2 is 15 meters per second. And you can see that here too, that after 1 second they had traveled 15 meters, like that. Okay? So in this unit we learned how to describe motion. Okay. So here are some key vocabulary words to know about. Motion is the process of changing an object's position over time. It's movement. The reference point is a place or object used for comparison to determine if an object is in motion or not. So basically it's kind of so if I'm at my desk, maybe that desk is the reference point, and then my position is like how far from the desk I am. Okay? And then we have distance versus displacement. So the distance is the total length of the path, that a moving object takes. So this whole thing, it'd be like the amount of steps you take, basically, is distance. But then displacement is the change in position from the object's final position to its starting position. So basically this is like the distance as the crow flies, meaning like not worrying about the path that they took to get there, just where did they start and where did they end. That's displacement, okay? So distance can be all kinds of crazy ways. It's whatever path you take, the number of steps you take, something like that. Whereas displacement is just as the crow flies, from here to here. And displacement takes into account direction. Okay. So we can use a reference point to determine if an object is in motion. So in this case, I would say that his floaty thing is the reference point there, or his slip and slide thing. Oof. Or you could say there's this tree here you could use as a reference point. So he's starting off at maybe like -5 feet from the tree, and he's getting closer and closer to that tree as he goes. For this one, we can think of this as a moving reference point. So the bear is moving, and the bear is moving faster than the duck. And that kind of thing would be really useful if you're determining how fast a planet is moving, or some kind of celestial body like that. I think I was